So we're in front now of the Metropole Parasol.
Or Las Setas in Spanish.
That's it. So in Sevilla, there are many monumental buildings, but what I really like is that there are also very modern structures, like this one, the one behind us, because it's only finished in 2011, so really quite new compared to many of the other things you can see in Sevilla. But the great thing is that when they built it here, they actually found Roman ruins below it. So it's a combination of all kinds of things you can see. The attraction is, of course, to get on top of it and walk over it, which gives you a great view. And we're now standing in front of it. Adela, I know that you are using the structure in your lectures, aren't you?
Yes. So the story behind this is that it was supposed to be finished in 2007, but 1 month before the due date, the information came that it was not possible, it was not feasible, because the basic project did not include technical tests, and there was not a technology to build this complex structure. So they had to substitute the metal and use instead wood. And yeah, so the mistake cost 28 million euros more than it was expected. And well, the lessons learned for my students is that it's necessary to perform a proper architectural design before you start implementing, developing a software application.
It's a good lesson, although Sevilla now has the largest wooden structure in the world, right? Which is also something.
Okay, that's it from my side.
Thank you, Adela. I think we all really enjoy very much these short videos and are super nice, really. Thank you for that.
Thank you.
Okay, so let's start the session. So the chairs of the session are myself, Andrea Buratin from the Technical University of Denmark, and Anna Kalenkova from the University of Melbourne, Australia. If you have any questions, please use the Q&A button that you can find at the bottom of the screen, and we will give you the word to ask the questions yourself. We have 4 very nice papers related to the data extraction, and I would say also the construction, the synthesis of data, as well as the validation and the analysis of these event data extracted. So without further delay, let's start with the first presentation, which is actually a collaboration between the FIM Research Center in Bayreuth, Germany, and the Queensland University of Technology in Australia. So Dominic will present the paper. So Dominic, the floor is yours.
Thank you, Andrea, for the introduction. I will just quickly share my screen. And please let me know when you can see it, and then I will start.
Yes, okay.
All right, then thank you again, and hello to the audience. So my name is Dominic, and as Andrea said, I'm a research associate and PhD student from the University of Bayreuth. And today, on behalf of my co-authors, I have the honor to present our research paper on enhancing event log quality, detecting and quantifying time-step imperfections. As the title indicates, we focused on detecting and quantifying timestamp imperfections in event logs, which are the main input for process mining analysis. And to get a feeling of how faulty timestamps might affect process mining outcomes, I would like to present 2 very basic examples. The first one that you can see now here is an exemplary case in an event log, in that the so-called issue mixed granularity is present. Mixed granularity means that different events are recorded with a different granularity. And here you can see that the first event, admission, is recorded until the second granularity, while the examination event is just recorded until the hour granularity. And if you have a look at the resulting process model, then you can see that process mining techniques would order these events as examination first, followed by admission, even though it's likely that these events happen the other way around, since normally the admission to a hospital should happen before a doctor examines a patient. The second example shows a basic event log containing multiple events recorded with the exact same timestamp. But in reality, the doctor might have conducted these tasks consecutively. But it is often the case that doctors fill in a form after the examination of a patient, and frequently this results in a record of all executed tasks with the exact same timestamp. And in the resulting process model, this means that the tasks are executed concurrently. I hope that the two basic examples recently shown have already shown that process mining results heavily depend on the data quality of event logs. But unfortunately, the reality is that event logs are often not of the desired data quality. And based on this conflicting interdependency, we concluded that an event log should not be naively used for process mining without first ensuring adequate data quality. And therefore, event log preprocessing is necessary. In terms of event log preprocessing, we identified several steps that are necessary. So first, the detection and quantification, and afterwards the remedy of the identified data quality issues. And in the end, the impact of the previous steps should be analyzed to come up with an improved event log. And in this quality cycle, we identified a research gap, because to the best of our knowledge, research that focuses on the quality assessment of event log is very limited so far. And we tried to tackle that research gap and intended to address the research question, how can we detect and quantify timestamp-related data quality issues in event logs? To reach our research goal, we followed the design science research principles by Peffers et al. And started with defining design objectives for our final artifact. Therefore, we first dived into related work and intended to discover, first, relevant data quality dimensions that we should consider, second, frequent event log timestamp quality issues that are already known, and third, existing event log imperfection detection approaches that might already exist. Due to time constraints, I will not explain our literature review in detail now, but these are the results of our literature scan. So we identified 4 data quality dimensions that are relevant for clustering timestamp issues: accuracy, completeness, consistency, and uniqueness. And furthermore, Suryadi et al. From 2017 identified 3 frequent event log issues, namely inadvertent time travel, form-based event capture, and unanchored event. And in addition, we also found existing approaches that already try to identify timestamp imperfections in event logs, namely infrequent relations, stacked or parallel events, mixed granularity of traces, or overlapping events. And interesting is also that these existing imperfection detection approaches already tackle some of the frequently happening event log issues that are already known. Based on these findings, we built our artifact. So the 4 identified data quality dimensions form the top axis of our artifact. The elements of the second axis are the common levels of an event log, namely log level, trace, activity, and event level. And this framework is now our foundation for the categorization of the addressed issues. And in total, we came up with 15 different metrics that are either based on existing detection approaches, modified based on other approaches, or newly designed by ourselves. And for the sake of time, I cannot explain every single metric, but I may encourage you to have a look in the paper, since each of these are well described there. We developed an automated detection and quantification approach that we also implemented as a prompt plugin, which I would like to present next. So the plugin is part of, let's start the video, yeah. The plugin is part of the Prom Nightly build and is therefore freely accessible. And for the demonstration, as you've just seen, we use the BPI challenge log from 2019. And after an event log is the necessary input for our prototype, and the prototype can be found by searching for log quality quantification. And after we start the plugin, every metric will be calculated, as can be seen here. And while the calculation is finished, a window will pop up showing the main window of the approach. And here you can see all of the 15 implemented metrics, and every metric contains a score and a quality level. And if the score is above 0.75, the quality level is high. If the score is between 0.75 and 0.25, we see the score as medium. And if the score is below 0.25, the quality level is low, which is indicated by the color red here, for example. In the top row and the left column, we also calculated scores for the quality dimensions and the log levels. And by default, these scores are representing the average value of the metrics that are linked to these dimensions or levels respectively. If you're interested in the events that are detected by a specific metric, you can access an error list by clicking the details button of a metric. And then after some time, depends on the length of the list will show up at the bottom of the screen. Hope it will happen soon. And there you can then see a list, because now we are searching for the error list for the metric precision. And then you can here see a list of imprecise timestamps, because none of these events contain a timestamp that is recorded until millisecond granularity. So here you can see that every timestamp has a 0 value for this millisecond. Yeah, the window, as you can see it here, is just a default configuration. So as different use cases and domains may require different weights and configurations, different metrics, different dimensions, therefore we implemented a configuration window that you can access by clicking the configuration button. Let's assume that for a specific use case, duplicates may be allowed and the timestamps are definitely of sufficient precision. And then you can untick the precision metric and the uniqueness dimension, as just happened. And furthermore, we assume that infrequent event ordering would have a huge impact on our results. And therefore, we use a higher weight for the metric. So we use 5 now, just for instance. And afterwards, we can apply the changes. And then the window will reconfigure based on the configuration. All right, so, and finally, we also implemented a create QAEL. QAEL stands for Quality Informed Event Log. And yeah, we implemented a create QAEL button. And by clicking this button, the identified scores will be added to the metadata of the imported XAS file. And I want to show you how this looks like in the next slide. Yeah. Here you can see how the data quality extension potentially could look like. So this extension is also depending on the last configuration that was made before clicking the Create QAEL button. So in the present case, it seems like the data scientist is not interested in completeness because there is no completeness dimension or completeness metrics. And precision is also not as important. As you can see, the precision is coming with a weight of 0.2. To ensure the real-world fidelity and validity of our artifact, we also conducted an evaluation using 3 real-life event logs. And therefore, we evaluated an event log first automatically by using the tool and manually by an expert. So, and afterwards, we used a Cryptognoss alpha and calculated the agreement of both assessments. So the automatic and the manual one. And if the alpha value was above 2/3, we assumed the agreement to be sufficient and proceeded with the next log in the same evaluation technique. If the alpha value was below 2/3, we redesigned the artifact based on a discussion with the expert and then started a new evaluation loop. An interesting thing is also that we conducted 2 passes through the evaluation cycle. So the first one was an internal evaluation, and here co-authors represented the experts. In this phase, we needed 1 reconfiguration of the tool or the approach and 2 evaluation loops to successfully finish the evaluation. The second one was an external evaluation. And here, experts both from academia and industry represented the log experts. And here we made it through the evaluation process in just 1 pass without any reconfiguration. All right, to conclude our work, I would quickly like to summarize the main contributions of our work. So first of all, we created a timestamp quality assessment framework and designed 15 data quality metrics structured along 4 data quality dimensions and 4 log levels. By using our approach, we also allow process stakeholders to assess the process mining suitability of event logs. And furthermore, the prototype assists data scientists in automatically identifying and assessing data quality issues by using the open source software that we provide. And lastly, we aim to raise the awareness for data quality in the process mining community by introducing a first step towards a timestamp-related data quality extension. All right, and now I would like to thank you for your attention. And if you have any questions, feel free to ask them now. Thank you.
Thank you very much, Dominic, for your nice presentation. I think it's very nice to see these works that are not only mining or consuming data, but that are also trying to assess the quality of the input. That's very nice. So do we have any questions from the audience, Anna?
Not yet. Not yet. So please ask your questions in chat and the question and answers.
Yeah. So maybe I can start with the first question, Dominic.
Sure.
Of all these metrics that you devised, is there any? Are these metrics also telling anything about, let's say, how we can fix the log or the logging, or are they just telling us? So what is the interpretability that we can attach to these metrics?
Well, I would say in terms of the remedy of the issues, it's definitely a first step that we already have that error list. So this also gives some information about which events are really affected by the identified issues. So therefore, definitely there is some information where to start with repairing the event log. So it's definitely, obviously, some future work that should be added, which is also shown in the recently shown event log quality cycle. Does this sufficiently answer your question?
Yes. I was wondering if you can get a bit more into some examples of what we might be able to get.
Yeah, so we're also trying to get some patterns, for example. So if we see, so in the future work, and if we see, for example, for the precision metric that I have just shown, we could first cluster for specific events. And if we see, okay, a specific event is always recorded with a, let's say, not as fine granular as desired, then we have like a methodology to repair multiple events within just small and easy actions. Yeah, and this was just an example. So we also try to do this for other metrics as well. As for each metrics, there are different ways of clustering the issues.
We have a question, one more question. So the question is there any motivation for the matrices you used in grading the quality in PROM below 25%, 50, 75, and above 75?
Yeah, so the question is why we used these thresholds for our log levels. Well, first of all, we made this configuration based on our evaluation. So our evaluation compared whether the automated approach detects low, medium, or high quality. And then we compared this to the expected evaluation by the experts. And based on this evaluation, we identified that these thresholds fit the best to represent the estimated values by the experts. And therefore, we used these thresholds. Yeah. We were also for sure thinking about using 1/3 or 2/3 as the thresholds. But in the end, it turned out that 25% and 75% fit the best to represent the thresholds that the experts would expect for the log levels, and not the log levels, the quality levels.
Okay, thank you.
Okay, is there any other question, Anna? Or
no question.
No. Okay, so thank you again, Dominic. I think we can move forward to the second presentation. Thank you. And we remain in the within the data level, and in particular, we remain within the time perspective of the data. And this paper is actually the collaboration of a group of Australian people, and it's among process diamond, the University of Melbourne, and Queensland University of Technology. And Adriano will present the paper. So Adriano, please, the floor is yours.
Yes, so I go ahead. Hello everyone, I'm Adriano Augusto from the University of Melbourne, and today I will give an overview of the approach we designed to repair same timestamp errors in event logs. So I would like to start with the central concept of this study. Is the event log is the data artifact that contains process execution data. The simplest of the event log is a table that contains at least 3 columns. The column representing the process execution ID, also known as case ID, the column representing the activity executed within the process execution, and the column representing a timestamp associated to the activity completion. Now, previous research studies have shown that as many other data artifacts, also the event logs suffer of data errors, and Boss et al. Classified these errors based on type of error and level of error. Type of error are missing data, incorrect data, imprecise data, or irrelevant data. The level could be at the level of the case ID, activity name, timestamp, or other attributes. Now, the focus of this talk will be on incorrect data and precise data that refer to the timestamps. Now, if we consider the event log I showed you before, here you can see that we have 2 activities that were associated to the same timestamp, so same timestamp error. Why this happens? Well, it could be because of the log granularity that doesn't manage to capture lower details of the time, or it could be logger errors when the logger records all the events in a burst, assigning to all of them the same timestamp, or it could be just a human error if the events are recorded manually in the event log. Now, the approach we designed is based on 6 steps. I will walk through all these steps in the next slide. So, given an event log that suffers of same timestamp errors, in this case highlighted in red in the traces, the first thing that we do is to generate a directly follow graph. So a graph where each node represents an activity and each edge represents a directly follow relations between the activities. The second step is to filter this directly follow graph, because previous studies show that every time you want to run any sort of analysis on a directly follow graph or event log, is always good to filter the infrequent behavior. So we apply this filter, and we remove the edges of the directly follow graph that are infrequent. Next step is to identify those edges that relate to directly follow relations caused by activities that are affected by the same timestamp errors. In this case, we highlighted in red in this directly follow graph. What we do is to simply remove them because they are not reliable, since they come from directly follow relations of events that were affected by the error. So after we remove these directly follow relations, we get the refined directly follow graph, and we'll use this refined directly follow graph to first fix the ordering of the activities that were recorded with the same timestamp, and then to assign the timestamp to the activities that were reordered. So first of all, we compute the confidence levels of all the edges, and the confidence level of an edge is the ratio between the frequency of the edge over the sum of the frequency of the edges having the same source. So in this case, for all the edges that have a source and node that has only one outgoing edges, so in this case, those are highlighted in red, the confidence level will always be 1. While for the remaining 2 edges, it will be 0.6 and 0.4, because this is the ratio between 3/5 and 2/5. After we compute all the confidence level for all the edges, we consider all the traces that were affected by same timestamp errors. In this case, we have 3 traces in the input log, and we repair the ordering of this activity. So that we consider the subsequence affected by the errors, and we compute all the possible permutation of the activities in that sequence. And for each of these permutations, we calculate the confidence of the whole subsequence. Finally, we selected the subsequence with the highest confidence, and we assume that to be the correct ordering of the activities. Now, for the second trace, since we have the same set of activities, we are not going to recompute all the conflicts because we already have it. And also for this case, we fix it using the same sequence. The last trace is composed only by two activities. And in this case, since we don't have any edge in the telefollow graph between D and C, its confidence would be 0, and therefore the correct resequencing of this couple of activity will be CD, that has a confidence level of 1. This exercise of reordering these activities within the subsequence is the most complex step of the approach, because we want to identify the most likely sequence out of all those that are possible. And this is an NPR problem. Likely, this problem is also equivalent to the maximum travel assessment problem. This problem has been investigated a lot in the literature, and it's available, it's ILP formulation. So what we did is, was to adapt the ILP formulation to solve the maximum travel assessment problem to our context, and we reused that ILP formulation to identify the sequence of events that is the most likely. After we reordered all the events, we can focus on assigning the timestamp, so the correct timestamp. To do that, focus on each activity that was affected by the same timestamp error. And we consider all the same activities in the event log that were not affected by the error. And we calculated the probability density function of the event duration, where the event duration is the time between the activity preceding the activity under analysis and the timestamp of the activity under analysis. So we assign finally the timestamp to the activity to repair simply as the timestamp of the activity preceding it, and plus a value extracted from the probability density function. So we evaluated our approach. We started from a process model that was an artificial process model, and we generated one single event log from this process model. And we injected noise at different levels of events, trace, and distinct traces at different percentage. We generated 24 corrupted event logs, so event logs that contain the same timestamp errors. We gave these event logs in input to our approach and two other baselines that we designed for the purpose of this evaluation, because there were no other studies addressing this same problem. And after we obtained the repaired event logs, we compared the event logs to the original event log, so the one that was not affected by any error, by calculating the Levenshtein distance of the traces of the event logs. So if we consider the results obtained from the repaired event logs when the errors were injected at the event level, you can see here that our approach was the one that was able to repair the most of the traces, the most of the errors. There is in black, so it sits well below the other baselines. And similar results were obtained when we considered the event logs where the noise was injected at the trace level. We also assessed the approach on real-life event log, and we used the event logs from the BPI Challenge 2014. That was the only event log affected by this type of error. We use the same framework for the evaluation, and also in this case, our approach outperformed the other baselines, so repairing the majority of the events. Finally, we also assessed our approach on a case study that was performed on an event log that was sourced by an Australian company that in the business of livestock. So the event log captured the process of the cows from breeding to slaughtering, and it contained 3,000 traces with almost 20,000 events, of which 30% were affected by same timestamp errors. And 2,748 of these traces contained produced a conceptual error that led to having the cows slaughtered before feeding before leaving the feeding lot. So here you can see that this is directly follow graph generated from the event log. You can see that the processing was performed before the feedlot exit activity. So we applied our approach on this event log, and the result was positive, and we were able to repair all the errors. Regarding future work, this approach only consider event logs that didn't contain life cycle of the activities. So a possible way to extend the approach would be to repair event logs containing also life cycle of the activities, or consider a different approach to repair different timestamp errors. So this was all. Thank you for watching, and if you have questions now, I can answer.
Thank you, Adriano, for your presentation. I think it's a very nice paper as well, and I think this problem that you tried to solve here, it's a problem that is becoming, at least it's my feeling, is becoming fairly common now, especially when you have maybe event data that is not so fast-paced. It's quite often that you have these issues, so yeah. So Anna, do we have any question from?
Not yet, so please ask, so we can unmute you. So please ask in chat or questions and answers, or raise your hand.
Yeah. So maybe I can start with a first question, if that's fine with you. And I would like to hear a bit more about the bias, I would say, that you are introducing when you are applying these corrections. I mean, when you are correcting, you are using some probability functions, which is based on the rest of the data. But you are also somehow applying some filtering on the DFG. And this filtering perhaps is also, it represents a bias essentially. So which threshold would you consider? So
yes,
can you comment a bit on that?
Well, the measure probably, there are two limitations in this approach. So the first thing is that we assume that the events affected by timestamp error are incorrect, but technically we are not 100% sure of that. And second, we can repair the events only if we have at least a few observations that are correct. So basically, let's imagine we have only events where that specific event or that couple of events is always recorded with the timestamp error. This approach wouldn't work because we don't have other data to automatically repair. And so these two are the measure limitation, of course. And in this sense, the approach is biased in the sense that, maybe biased in the sense that we assume that the event affected by timestamp error are mistaken in the first place.
Yeah. Okay. Thank you.
So also I have a question. Talking about DFGs, how do you deal with parallel processes? So does the approach work better with sequential models, or for parallel it also works good?
I'm not sure. So no, I mean the approach doesn't repair the final model. Actually, we just repair the ordering of the activities, and if some of the activities are in parallel, the order would be repaired according to the other observations, of course.
Okay, I see. So we have one more question. Let me unmute. Yes. So please ask your question. So unmute yourself. So now you can unmute yourself and you can ask. Jing Yang. Yeah.
Can you hear me?
Yes.
Yeah.
Right. So I just have one quick question about the evaluation done on the artificial log. I noticed that in one of those figures, the baseline method naive repair seem to lead to a result that is with higher Levenshtein distance from the original log compared to the input corrupted log. Does that mean that the naive repair actually has done something even worse than what you expect?
No, so yeah, I understood the doubt. So the thing is that I think you are referring to this table, right?
Not actually. So there's a figure showing the lines that that represents the trends of the Levenshtein, the trend of how the Levenshtein distance varies according to how much corrupted information you inject into the log. I think that's the figure that I'm referring to. So probably the slide before this one. Yeah, on the artificial log. Yes,
This one?
this one. So, so that's the sub-figure C, where I noticed that the naive repair methods have actually generated some worse result than the original affected log, and I wonder.
So here there is not the original log, because the original log, the one that was not without injected noise, was the one used for the comparison. While here the one that is called affected log already has some noise. So basically, we are compared the log with the noise and I guess the original log, and then the log repaired with naive repair to the original log as well. So here there is this one that is called affected log is not the original log actually.
Okay, thank you.
Okay, thank you. Do we have any other question, or can we move forward?
No.
No.
We don't have any.
Okay, so thank you again, Adrian.
Okay, thanks.
Thank you. Okay, so we now slightly change topic, but we're still within the domain of, let's say, manipulating or constructing data. So the next paper is actually about constructing event logs from videos that are tracking what is happening. It's actually a paper coming from the German Research Center for Artificial Intelligence, the FKI in Germany, and Sönke will give the presentation. So, yeah, please.
Okay, can you see my slides?
Yes.
Okay, yeah. Thanks for the introduction. So today I'm presenting the video to model approach, and this work has been conducted together with my colleague Sriraman, who conducted his master thesis in this field, and with Tim, who's the head of the Human Robot Collaboration Lab, where we tested our approach. So first of all, we are facing a scenario in assembly, so a manual assembly process at a workstation, which you see here on the right side. So usually there's a worker having different materials and assembling a product according to instructions on a screen, how you see it on the image. And such assembly processes usually consist of work steps where material parts are involved and tools are used for the assembly. So now, if we want to generate a model about such a process, this means high effort to the company. Yeah, so they are conducting observations. They are conducting interviews and workshops with the workers together to identify potentials for improvement. And here we see process discovery as a nice data-driven alternative to automate this process, accelerate it, and make it even more cost efficient. So the goal is to have a meaningful log about such manual assembly processes. Therefore, we use sensors, and the challenge is to generate event pieces that can be used for process mining. So on the left side here, you see the assembly workstation we used. It's built based on industry standards. And here on top, I hope you can see my virtual laser pointer. You see the camera, which is looking from the stop perspective down to the assembly workplace and observing this part. And here on the lower image, you see what the camera sees. So it sees these material boxes, which are common to provide the materials to the user. And here's an assembly place where the parts are fixed and assembled together. And we only see the hands of the worker. And now if we receive the stream from the camera, we store that data and want to extract information about hand locations, use that to build a trajectory consisting of multiple hand observations, so representing the grasp path. We cluster those trajectories and finally assign a work step ID to it. So now let me walk through these steps. First one is the hand detection. So here we use object detection and localization from computer vision. This delivers usually a bounding box, as you see it here on the right in the image, and delivers information about the hand's position within the image. So those detectors are nowadays using deep neural networks, and we use the famous detector YOLO-V3, which we trained with an EGO-hand data set, which consists of videos from an egocentric camera, and the Viva hand detection challenge data set, famous also in the community, consisting of YouTube videos and videos about showing hands of car drivers. So once we have those hand positions, we're now building the trajectories, as you see it here in the lower image on the right. So there we have these different points, and these points refer to one observation of the hand. And it's the midpoint actually, which we call the pivot point, at the top horizontal edge of such boxes. And then we have a criterion how these boxes are overlapping and how distant the pivot points are. And if the criterion holds, then the next point is added to one trajectory, and then we receive this characteristic shape, because it always starts at the assembly zone and ends there. And this is what we then call a trajectory and how we understand a work step. So here you see the system in action. On the left, the worker is grasping materials. And on the right side, you see those trajectories. So the video was recorded and the processing is done offline. It was recorded at 60 frames per second. And in this way, we can compute the trajectories. So after we have the trajectories, then the next step in the pipeline is a clustering to cluster trajectories which share characteristics. And here we use hierarchical bottom-up agglomerative clustering. And you see then that we receive these different clusters of trajectories in different colors here. So for each class, there's a separate color. And now we have the problem that different clusters refer to the same box. So they would belong to one box step, but due to the difference, because they were executed with the left hand, yellow, and in purple with the right hand, they belong to different clusters. And in the next step, we are now assigning them to the right work step ID. And there we introduce a voting procedure. So we have usually in an assembly setting always information about the box position. And we use this information. So we have these locations where a box stands, for example, box 1. And now we calculate the point of one trajectory, which is most distant to the assembly zone, and calculate the distance to the left or right side of such a box. And in this case, those both clusters are now assigned to box 1. So this is what we call work step identification. And now we have assigned the ID, the correct label to all of those traces. So here's the full pipeline again. So you can see it starts at hand detection. We build trajectories, cluster them, identify the work steps using the assembly setup. And what we finally receive is a process mining log, as you may know it. So here we have the different labels, and we also have information about the person, which has to come from a staff management system, and about the product, which might come from an out ID system. And here, for example, we see that we also had a ground truth log, which indicated the ground truth. And for example, here was a junk path. So the hand movement here was not correct. It was not belonging to the box, but it was assigned to a box. So this is one of the problems, or a repetition. So when a trajectory was broken due to a missed hand detection. Yeah, but let me explain or say a few words about the evaluation. We had two different setups here on the right. One simple setup where things were assembled from left to right, which is usually done in an efficient way, and one more complex setup where there were also first more boxes, and second also bulk material like screws involved. We conducted the experiment inviting 10 participants to assemble such products in a task-based way. That means they had clear instructions how to assemble the products. And this was also modeled as PetriNets, which we call the reference model, the model ref. So that was what we introduced to them. And then we had as already mentioned, the ground truth log, where manually the assignment of work step was done to the trajectories. And we had the discovered log, which we load into PROM using the inductive miner. We then generated a model, the discovered model. So this is what the supervisor of such a manufacturing would be interested in. And now we did two comparisons. So we used conformance checking to show how good the approach performs. So the first comparison was the ground truth log against the reference model, so based on the instructions. And we made two assumptions for that. So the participants had clear instruction to follow those reference models. And the log ground truth, as explained, indicates what could have been discovered, so the potential of the system. And now if we do the conformance checking here, we see how good hand detection and trajectory building actually performs. The second comparison was the ground truth log against the discovered model. So the discovered model is kind of a representation, aggregated representation of the result of our technique, which generated the log. And if you compare this against the ground truth log, we receive information about how good trajectory clustering and work step identification, so the last two steps, perform. And here you can see that this, in task one, they had to do everything in sequential order, and the model also represents that. Here, two parts had to be grasped in parallel to accelerate the process a bit. This was also correctly discovered. And finally here, in task three, participants were totally free to assemble in the way they want, and they decided, the majority decided to follow task two and do the more efficient assembly. So it shows that the approach seems to be a suitable method to provide insight into manual assembly processes. Another way of looking onto the results is looking onto a confusion matrix. So here you see for the simpler setting, we have a very high accuracy with about 95%. And for the more complex setting, it was a bit lower, but still good with 89%. And we see that, for example, the boxes where bulk material was here created a lot of events. And there was also a confusion between box 5 and 6, which are here in a row. So there's also a limitation. If you place the boxes very close to each other, it's of course harder to detect and differentiate between the trajectories, the grasp path of the worker. Okay, so finally, we showed how to extract event data from really unstructured data, so from video streams, and how to bring structure into this, make it, transform it into information, and which can be used for process mining. It was achieving a very high accuracy, even with a very small sample size, so we think we can improve it if we would do more tests with more participants. And finally, the learning was unsupervised, so there's no very high effort for training necessary. And the logs were also uploaded on Figshare, so you were able to use them for process mining and try to get even better models. Finally, also the setup is very simple. It consists of one camera, so it could be applied also in temporary and even in small companies. And it would be maybe also interesting to think of other manufacturing, of other use cases as manufacturing, for example, in the logistics domain or somewhere. Okay, thank you very much for your attention, and looking forward to your questions.
Thank you very much for your nice presentation. I think it's very nice to see these techniques for synthesizing, let's say, logs. I think this can really unleash new opportunities for process analysis and yeah, data-based observations. So Anna?
Questions are welcome. Do not see any questions yet, so
okay.
Please ask questions.
Yeah, if you have questions, again, use the Q&A or the chat. But maybe I can start with some questions. First of all, can you maybe characterize which classes of activities these techniques can be used? I mean, hand detection is the main driver here. So are we essentially talking about all the activities that require to have a hand visible, or could we apply the same, for example, if we have a camera looking at a whole warehouse, for example, and looking at the persons moving over around shelves or workstations?
Yeah, thank you. That's really an interesting question we have not thought of so far. So I think we just need observations, and which are of a nature that they have a starting point and a goal, and in this way they are also repetitive, yeah, in nature. But I think if we have such things also on the shop floor, looking from a more far distance, that could be also interesting, and I think yeah, it would be quite interesting to apply it also to such a scenario and see how good it performs. But yeah, you're right. I mean, it could be applied to other observations as well, and where you have successive points you want to connect, and you want to analyze or search for optimization. Yeah.
Thank you. That maybe let me follow up with another one. Anna, if there's any question, please interrupt us. So
okay. Mm-hmm.
Yeah, I think
no questions yet.
No questions yet. That's okay. So I think I was missing a bit the reason why you needed to cluster the trajectories instead, for example, of just identifying when a hand was entering, let's say, the bounding box of the visual bounding box of a physical box, if you see what I mean. So what is the advantage of using trajectories over a more, let's say, visual approach?
Yeah, we had in previous work actually also another approach where we had more like reference points. So we just looked for activity at a certain point and then connected different activities to the process. But here our intention was really to have something where we can observe with one camera in unsupervised way a grasp path. And here at the very beginning, we only need the hand detection, and until here we have no information about the boxes. So
right.
we understand really the grasp paths, and by this I forgot to say that we also receive information if the right or left hand was used very accurately. But then finally we use this information only for the labeling, because we thought, okay, usually those setups are very strict, and why shouldn't we use it? But until this point, it's totally free of any setup. So it's it's working like only on the camera image.
So would it work also if, let's say, the physical box is moving around a bit?
Yeah, it would. A bit is
yeah.
It depends on how much is a bit.
What is the bit? Yeah.
Of course, if you change the bits or the boxes, it would be quite difficult. But still, you would collect information about the graph path only then, and it would be hard to establish a connection to the actual materials involved, and therefore you would maybe use another object detector to identify the materials or something like that.
Right. Thank you.
So there is one comment and one question. The comment is that this is a very cool work. And the question, so now I will unmute. So please now you can ask your question.
Hello. Yeah, can you hear
Hello.
my voice?
Yes.
Yes.
Yeah, so thank you for your presentation. So actually, I'm also working on the same process like yours, but I think I use the different sensors. And my question is, how can you decide the model reference?
The reference models? Yeah, so the reference models were what we instructed the people to do. So we really, we had 3 tasks in total. The last was the free tasks. They could do what they want. So the most difficult for us, for the observation. But the first 2 were clearly instructed. So they should take material from box 1 and box 2, assemble them, take from 3 and 4, assemble them, and so on. So this was, the reference models were modeled by us, so by hand. Manually, to have a comparison.
Okay, thank you very much.
Okay, I assume we don't have any other questions. So thank you again, Sönke, for your nice presentation.
Yeah, thank you.
So we can move to the last paper for this session, and somehow we still remain within the connection to the physical world. So sensors capturing what is happening in the real life. But now we move to the online domain, and we will hear about the concept drift in the online sensors data. This is a work from the team at the University of Vienna, and Florian will present the work. So Florian, the floor is yours.
So is everyone seeing my screen?
Yes.
Okay. Good. So thank you for the introduction. My name is Florian Sterz from the University of Vienna, Research Group Workflow Systems and Technology. And today I'm presenting our work on analyzing process concept drifts based on sensor event streams during runtime, so online. We are from Vienna, so at the background you see one of these forest cities that are apparently now everywhere in social media, so that you can have some local culture. And now let's start with our paper. So we start with a little bit of an introduction. What is the motivation of our work? Business processes need to adapt constantly. So process models get changed, the rules get changed. So for example, the data elements inside this task can change. And these changes are done to the process model. If something happens during execution and you detect it, then it's a concept drift. There's some finer granularity in the drift, could be in the workflow perspective, so in adding or removing or different events or tasks in the process model. It could be also on the data perspective. So for example, if instead of only some resources are allowed to execute a task, maybe other people or other resources are allowed to execute a task as well, or an even stricter approach. For example, GDPR introduced lots of concept drifts since many process models had to be changed in different kind of ways. And there are a plethora of techniques available to detect concept drifts already, online, offline, process histories, tesseract, whatever they are called. And our main motivation was now we know that the drift is happening. We first want to see detect the drift as soon as possible. So we want to do things online, working with an event stream instead of process execution log. And the other main motivation is, why is a drift happening in the first place? Can we detect that? Can we find a reason for a concept drift? So for example, we have here a very simple process model from the medical domain. We have the process model A is the first process model, and it drifts into the process model B. So at the beginning, we have check patient, and the blood pressure is taken, and some drugs are administered, depending on the status of the patient. And suddenly, all the newer process instances of this process model also show a new task, the check hydration. And what we see as well is that apparently nurses now also are taking the blood pressure, not only medical doctors. So why is check hydration now added to this process model? Could be just a wild guess that someone thought it was a good idea, but maybe it has something to do with the environment. So for example, maybe we switched from winter to spring or summer, and where we have usually higher temperatures and the air is more dry, and where that the hydration should be checked more often. So a concept drift, maybe even a recurring drift if it happens always in the summertime, is happening. And we can see if we check the temperature all the time in a patient's room, for example, that a rise in temperature would be detected as well. So there would be a drift detected here as well. So what can we now take from our small example? That external sources can influence the process. So for example, the temperature, humidity, others from the industry domain, production domain that we will be showing at the end of this presentation. The problem with sensor event streams usually compared to these process execution log event streams are that they are not captured inside of the process execution. So they are captured outside. You have your process execution, maybe controlled by a process execution engine. And there are some sensors placed in the patient's room in our little example that are protocoling the temperature and sending it to some device, to some database, where it has nothing to do usually with the process instance, so the patient's inside of this room. And they're usually stored in time sequences. A time sequence, in our case, reflects the measurements of the temperature here, for example, in degrees Celsius at different timestamps, so a specific time intervals, 21 degrees, then after some seconds, again 21, 24, 24, 27, so it gets a little bit warmer, a little bit colder, maybe depending on the day of the time of the day. And so we try to find our research questions for this paper. So how can drifts in sensor streams, sensor event streams, associated with process instances be identified? So we have now our event stream. We have our sensor event stream. So the sensor is producing time events. How can they be associated with each other? And how can a drift in the sensor stream be associated with drifts in the process instances and process model? And the other very important question is, what do we gain from it? So how can an analysis of these drifts help domain experts to assess root causes and thus propose concept drifts process evolution? So if we already detect really that the temperature is rising, so we see the drift in the future time from, for example, the temperature, how can domain experts react fast enough, maybe even prediction that we need a new concept model and thus propose a concept drift? So how can we use these results that we gathered from research question 1? Our contribution consists of 2 components. We have our time sequence module and our drift decision detection model. So when we look at our architecture, we're using the process history, which shows the evolution of a process model and during the runtime. So it captures all the concept drifts that have happened beforehand. and is attached to a process execution engine and is working with an event stream. We are having some sensors, for example, the temperature or other. In our real-world example, it will be the measurement from the diameter of some production parts. The source of a concept drift does not have to be only one data stream from a sensor. It could be different sensors with different data streams. So everything is put inside the process history module. So therefore, sorry, every time a concept drift is detected, so when we have seen at the beginning from A to B, the time sequences that are tried to assign and correlate to the process models are put inside the time sequence model, and the average time sequence for different events or for the whole instance are generated for this whole process model. For this, for example, we are taking the sensor data stream and slice the part out that is fitting different events out of this process model for specific tasks, for example. And every time a drift happened, we are checking the average time sequence that is attached to the process model now with the drift decision detection. And then the drift decision detection module is therefore detecting if a drift happened or not. If the drift happened only in the process model or also in the time sequences. For example, there could be, of course, concept drifts that are not attached to any sensors that we know of, for example, GDPR. A little bit more in detail, how are we detecting this average time sequences and how are we calculating the similarity and difference between different time sequences? So we receive the time sequences from the process history and we calculate the average time sequences based on the dynamic time warping barycenter average algorithm. What dynamic time warping is, we'll go into detail on the next page. It's a very fancy name. The returns for each process model and data stream, the average time sequence. So this is what will be returned. Why are we using dynamic time warping and not something more simple like Euclidean distance? A problem with the sensor data streams is oftentimes that they have a different amount of data points and data values. And dynamic time warping can negate this issue. So it can calculate the similarity between two sequences that have not the same length. So in this example, how does the dynamic time warping work? We have then sequence A, 28, 25, 25, 28, 28, and so on. And we have the time sequence B, 27, 25, 25, 27, 27, and so on. You calculate the difference between the cells in the same row and column. For example, 28 minus 27 is 1, and you insert the 1 here. If you go here, it would be 25 and 27, the difference is 2. You take and add the smallest cell that is either on the left, on the bottom, or left bottom. So here it would be 1. A more practical example would be, for example, here, 27 and 28 have a difference of 1. The minimal cell that we are looking into is here. 1 plus 1 equals 2. And if you go at the top right cell, you have the cost, dynamic time warping cost to go, or for alignment cost if you want, to align one time sequence to another with the dynamic warping path. And the dynamic, not our, but the dynamic time warping barycenter average algorithm is used since we want to compare one average time sequence for one process model for one sensor to another one. So, for example, it's works like this. So we have 4 different time sequences, and we store this average time sequence in the process model. The drift decision detection receives then the process models that were detected in the drift. So in our first example, it would be process model A and process model B. With their specific average time sequence, hopefully there would be, for example, an increase in temperature. So the the average time sequence of the newer process models of process model B would be higher and would exceed from experts defined threshold. So the drift decision detection would detect a verified drift also in this sensor data and returns the result of the drift detection. We evaluated this on a real-world data set. We have prototypically implemented it using our research group's process execution engine, the CPE. I've implemented it and working with a real-world data set. So in this data set, there were 776 data points on average. And what we used was a sensor for measuring the diameter of a small production of a part of a gas turbine. So a small part from a gas turbine was produced. I have to say it was produced in sequence. So even though therefore it, we had in one batch, we looked into one batch, so 34 pieces were produced in sequence. The measuring was taken place before was when the part was put through a laser to measure the diameter of the whole places from this part, and afterwards it would be controlled by a human being, which is of course the more expensive part, to use a human being to detect if a part is correct or not, instead of just putting it through a laser. So what can happen during this production? There could be physical effects to deteriorating machining tools, for the drill is not sharp anymore, or temperature fluctuations, which has some impact on the material. And the problems then would be stemming that there are some accumulating debris that affects the production quality as well as measurement quality. For example, here is pretty clear that some debris are accumulating on the side of this little part, and this would be a clean part. Not all of these faulty parts are detected as easily. So what we want to prove now is that if there is a drift of this production, for example, that in the end there would be a data drift because all of the products would be turned out faulty instead of good. Would there be a drift in the sensor stream as well of the laser measuring part? That would be identified as the reasoning. So if we find enough drifts inside of this measurement, will there be a concept drift happening at the same time? So out of our 37 parts, 18 parts were faulty, which led to data drifts in the process models on the data perspective. And we could detect all of these concept drifts to a drift in the external sensor with, of course, some changing of the parameters. It depends on, usually when you're doing stuff online, how many faulty instances you're comparing. So when you do the averaging of the time sequences, how many faulty instances or how many currently produced, last produced instances are being looked into for the average time sequence. For the more detailed with the table how the parameters are set is in the paper. And of course, what was the main benefit of this adventure? The experts expanded the process model with a check. So before the manual check of this little gas turbine part has to be done, the result of the measurement with the laser will be taken into account, and there will already be declared as faulty parts before you have to make the time-consuming part of a human interaction. And of course, if it happens too often, you can figure out why the measurement yields wrong results. Maybe change the drill or check the temperature in the workshop room. Thank you for your attention and hope for some questions.
Thank you, Florian, for your presentation. I liked your work very much, not only because it's online, so I like very much this idea of online data analysis and process mining, which I think is very relevant. but also because you're hinting towards this sort of explainable or explainability of behavior, which I think is very nice as well. Anna, questions? I would like to predict no, but
No questions.
no questions. But yeah, it's a bit late, but maybe I would give a couple of minutes to the audience to see if there's any question. And in the meanwhile, I would like to ask you a first question, which is that you were actually talking about some thresholding or some parameters configuration.
Yes.
So I was wondering if you can say anything about that, and in particular, if this parameter tuning is something which has an interpretation as well, or if it's just a magic number that needs to be set by some wizard or something.
There are different parameters. One, for example, one parameter is definitely when is averaged the time sequence different to another. This depends. So the distance between one sequence to another, this can only be done by either iteratively way or an expert, but it's hard for me myself to imagine that someone can say, yeah, if the time sequence differs from this value, then it's a drift. So we have done it iteratively to see how the parameters should be set. We tried different settings. And the other one, which is more intuitive, is of course for the process history. So when you work online, you have only a limited number of space and memory in your computer, so you can't use all the traces that had ever been executed. And you're usually maybe working with a sliding window approach where you removing old traces and only looking at newer ones, for example. These parameters have to be set according to different machines, and of course a little bit of the nature of the processes, for fast living process or if it's processes that are running for years, for example.
Yeah, of course. Yeah, okay, thank you very much. Anna, any questions? No. Okay, then since we're already 2 minutes over our session, I would like to thank you again, Florian, for your presentation. I would like to thank all people who attended, all the presenters for the very nice papers and the nice presentation. Now, according to the program, there's the coffee with the authors. And then in roughly 20 minutes, 17 minutes from now, there's the panel. So see you there and have a nice day, evening, morning, whatever. Bye.
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 Bye. Bye.